Good morning, dear students. My name is Ferhan Mazher, and today is 31st December 2021. And today is the last day of the 2021. And from my side, Happy New Year to everybody. We are studying the subject of Physics 5054, and I am right now with the 11 Cambridge class. Today we have selected a theory paper. We call it paper 2. We have selected May-June 2018 2-2 paper. This paper belongs from the zone 2, and in this session, in this video, we will solve its section A. So let's start this paper. So we have May-June 2018 2-2 paper, and today we are going to solve its section A. It's a theory paper. The total time allowed is 1 hour 45 minutes. The section B of this we will solve in another paper, in another video, in another session. Okay, so section A. A student drops a small metal object into a cylinder of oil. The object falls alongside a vertical ruler, and a camera records its position at time 1 seconds intervals as shown in the figure 1.1. So basically what is happening, they have dropped a ball into this cylinder. This cylinder is filled with oil, and they have placed a scale also there, and they're recording it. So they are checking the location of the ball after every 1 second. So because they are doing it with the camera, so it's quite convenient for them to record the position of the ball after every 1 second. Okay, so on the grid in the figure 1.2, plot a distance time graph for the object. So here we have to draw a distance time graph. And here you can see the distance is represented, which the ball has covered inside the oil. Here we have time interval, the time in seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So from this, I can tell you that at 0, the position was 0. At 1 second, the position was 0.5 centimeter. At 2 seconds, the position was 1.6 centimeter. Sorry. At 3 seconds, the position is 3. You can say 3 centimeter. And at 4 seconds, the position is 5 centimeter. And at 5th second, the position is 7 centimeter. So these will be acting like coordinates, x coordinate, y coordinate. The distance will be the y coordinate. I will plot these points on this graph paper. It's a distance time graph. It's a 2-mark question. Let me show you. Okay. So this is that, and this is the points which I plotted: 0, 0, 1, I think 6, and 2, something, then 3, something, and 5, 4, and then this is 5 at the 5th second. The position was 5 centimeter. So I plotted these points. Hopefully you can see these red dots. Can you see that red dots on your screen? Okay. Now, this is, I have tried to join them with the help of the mouse, and it's a curve. Okay. So here I have shown that diagram. I have drawn it on a paper. So if you have the hard copy of this paper, then it's very easy for you to draw them. Just plot those points and then join them with a curve. This will automatically make a curve. Okay, so that was a 2-mark question. Okay, now the B part is that the object has a constant speed for some of the time. State and explain how a distance time graph shows that the speed is constant. You see, if this is a distance time graph, the slope of the distance time graph is equals to the speed of the body. We are talking about distance time graph, remember. The slope of the distance time graph represents the, so it's a distance time graph, and the gradient of this distance time graph is equals to speed. So if the speed will be constant, it mean that the gradient will be constant. And when the speed time graph will have a constant gradient, the graph will be a straight line. The gradient will not change. So hopefully you understand what I'm talking about. Constant speed is shown by constant gradient on the distance time graph. Gradient of the distance time graph represents speed of the body. So this is the answer. So let's move to the next question. Then he says, explain in terms of the forces acting on the object, how it is able to fall at a constant speed. You see, the ball's weight is acting downward. You see this ball? These balls, they are in the oil, they are moving inside the oil. And their weight is acting downward. And obviously, when they move through the oil, what happens? The oil will resist their downward motion. So the oil is providing the drag. It's giving the resistance to the motion. At some point, because the ball's velocity will be increasing, at some point what will happen, the more the velocity of the ball, the more will be the drag of the oil, the more will be the resistance of the oil to the motion. So at some time, what will happen, the drag of the oil or the resistance of the oil to the motion of the ball will become equals to the weight. So the resultant force will become zero. When the downward and upward force will become equal to each other, the resultant force will become zero. So the acceleration will become zero, and that's why the body will move with a constant speed. Let me show you my answer. If weight is acting downward, air resistance is acting upward. This word air resistance is not the right word, because when I wrote the answer, I was thinking that it was moving in. Here, this is oil. So here you, instead of using the word air, use the word oil. Resistance is acting upward. During fall, velocity increases, and due to this, oil resistance, instead of saying air, say oil. Okay, oil resistance increases. When the oil resistance, the resistance of the oil to the motion of the ball, resistance becomes equals to the weight, resultant force becomes zero. So body will have zero acceleration, and it will fall, or it will fall in that cylinder at a constant speed, because the net force will become zero, the acceleration will become zero, so the body will fall at a constant speed. So hopefully you understand. So that's the answer. Okay, so let's move to the next part. Okay, so the question number 1 is over. So before we go to the next question, let's have a look at the marking scheme. My dear students, on your screen, you can see the marking scheme of the question number 1 showing up. It's May, June 2018, 2-2 paper. Question number 1, and you can have a look at the marking scheme. You can pause the video and you can take your time with this marking scheme. And remember, always, I'm telling always, whenever we are checking the answer, it's very, very important to check, to match your answers with the marking scheme. Okay, so let's move to the next question. I have already checked these answers, and so let's move to the next part. In an experiment, a student takes measurements and determines the extension of a spring for different loads. The apparatus is shown in the figure 2.1. So here we have a spring. Here you are putting loads. So if they put loads and they note down how much is the extension. How much is the length, and from there you can calculate the extension. The table in the figure 2.2 shows the results. So when there is zero load, the length of the spring is 200. When there is no load, the length of this spring here is 200 millimeter. When you put 1 Newton load, the length becomes 235. When you put 2 Newton load, the length becomes 270. When you put 3 Newton load, the length becomes 305. When you put 4 Newton load, the length becomes 350 Newton. And when you put 5 Newton load, the length of the spring becomes 420 Newton, 420 millimeter, sorry. So this third row is extension. So I can find the extension. I can calculate the extension. How you calculate the extension? The length at that load minus the length when there was no load. We say L minus L naught. The length of the spring at a certain load minus the length of the spring when there is no load. So if you want, when you put 1 Newton load, you want to find out what is the extension from the length, this moment, minus the length when there is no load. So 235 minus 235. For example, when the load is 2 Newton, the length is 270 millimeter, and you want to calculate the extension, the formula for the extension is L minus L naught. So L here is 270 millimeter and L naught is 200. So 270 minus 200, that will be 70. 305 minus 200, 105. 350 minus 200, it will be 150. 420 minus 200, it will be 220. So this is how you can fill this extension. Only some of the extensions are shown in the table. Complete the table to show all the extensions. I hope you understand. I have shown you. Let me show you now. I have done this on a paper also. Let me show you. Okay. So on your screen, you can see this red, this column I have filled here. This fill in the blank. This blank box I have filled. How you got 150? 350 minus 200. This length minus unstretched length. How you got 220? 420 minus 200. L minus L naught. So I hope you understand this. So this was a 1 mark question. Okay, so let's move to the next part. Calculate the load that produces an extension of 49 millimeter. So we have to calculate the load which will produce an extension of 49 millimeter. So let's see. You know, one thing is very technical here. So here the load is increased by 35 newtons. 35, kind of 35. Sorry, the load is increased by 1 Newton. The increment in the load is uniform. 1 Newton you are increasing. But the extension you can see here 35 increase. Here the extension further increased by 35. Here again 35, but here it has not increased by 35. So here somewhere you have the limit of proportionality. So before this load, the extension and the load, they are directly proportional to each other. It's very important point here that up to 3 Newton, the extension and the load, they are going directly proportional to each other. If you double the load, the extension also becomes double. They are proportional to each other. But after 3 Newton, you see you increased from 3 to 4, you increased 1 Newton further, but the extension is not 35. The increase in the extension is not 35. Increase in the extension is 45. So the extension and the load, they are no more directly proportional to each other. So before this 3 Newton, the load and the extension, they are directly proportional to each other. So now the question is, what load will produce an extension of 49 millimeter? So you know that the load and the extension, they are directly proportional to each other. So I can use that proportional method. Let me show you. Let me show you. Okay. So I have taken the values load and extension. They are directly proportional to each other. So I can use the method of proportional. 1 Newton produces an extension of 35 millimeter. So how much X load will produce an extension of 49 millimeter? So I can write this in the ratio 1 by X is equal to 35 by 49. I can write it in the fraction. So cross multiply X will be equals to 49 divided by 35. And that will be 1.4 Newton. So if you will put a load of 1.4 Newton, there will be an extension of 49 millimeters. Hopefully you understand. One very technical thing about this question is that you have to take this value, this load and extension value from that portion of the table where the load and extension, they are directly proportional to each other. You have to remain below the limit of proportionality. Okay, hopefully you understand. Okay. A student pulls a load downwards from position A to position B and holds it fixed at the position B as shown in the figure 2.3. The load is stationary at A and at B. The load has no kinetic energy at either point. Place ticks in the boxes to show how the value of each of the form of energy compares at A and B. So first of all, energy stored in the spring. So here at the position A, the spring is not stretched. But in the position B, the spring is stretched. So it means now it has the stored energy in the spring. So the larger stored energy in the spring will be at the B. So put a tick here. Then he said gravitational potential energy at the of the load. Here the height of the load is larger, higher. And here the height of the load is from the ground is smaller. So less height here. So here, because the height is larger for the load will have higher gravitational potential energy in the position A. So put larger at the A. Put a tick here. Let me show you. So hopefully you understand that how we came to know that at which position it has the larger stored energy in the spring, and at which position it has the largest gravitational potential energy of the load. Okay, now, so let's move to the next part. Work is done by the student to pull the load down. The law of conservation of energy states that energy cannot be created and cannot be destroyed. Explain how this principle applies in this case. You see, when a student has pulled it down from position A to position B, the student has chemical potential energy inside it. The student has chemical potential energy. So when he worked, he applied his energy. So there will be a decrease in the chemical potential energy of the boy. The load has gone down in the gravitational field. It has gone down. Its height has decreased. So the load has also lost gravitational potential energy. The boy has done the work in pulling it downward. So it has lost some chemical potential energy. The load has gone down. So it has lost some gravitational potential energy. But the spring has been stretched. And when you stretch the spring, you have to do work. You have to pull it down. And the spring has a restoring force. And when you pull it downward, you have to do work against that restoring force. So that work is stored in the spring. So the gravitational, the elastic potential energy of the spring has increased because you have stretched the spring. So the work you have done, the student has done to pull it down, to stretch the spring, that work has been stored in the spring. So the chemical potential energy of the buoy, the gravitational potential energy of the load has decreased, but the elastic potential energy of the load of the spring has increased. So the energy has converted from one form to another form. The total energy of this system will remain constant. It will convert from one form to another form, but the total energy will remain constant. It's a 2-mark question. A lot of I have given you a lot of explanation. Okay, so I have written this answer, but this answer is very lengthy. But just read it and write a better answer. I have explained the answer. The answer which I explained is better than what I wrote there. Work is done by a student in pulling the spring. That work done is stored in the spring in the form of elastic potential energy. Students' chemical potential energy converted into elastic potential energy of the spring. Gravitational potential energy of the load has decreased, and of the spring I wrote here, but the better word here is instead of saying spring, write load. LOAD. Okay. The gravitational potential energy of the load has decreased. Chemical potential energy of the student has decreased. Total energy of the system remains constant. Hopefully you understand. And let's move. Okay, so keep this. So let's have a look at the answer. So we are done with the question number 2. And let's go to the check the answers. Okay, so the marking scheme is coming up on your screen. You can see the marking scheme for the question number 2. Please pause the video and take your time and read this marking scheme very keenly and carefully. Match your answers with this. Okay, see which points you missed, which points you have written. So 150 and 220 in the table, any use of the proportionality, 1.4 Newton should be the answer. First line larger at B and the second line larger at the A. Student loses energy, chemical energy decreases, or gravitational potential energy decreases, and the spring energy increases. Idea that increase in the spring energy is more than the change or decrease in the gravitational potential energy. So student provides work needed. So the energy which is stored in the spring is more than the decrease in the gravitational potential energy, and so it means that the difference is coming from the buoy. He provided actually the work. He did the work which was actually converted into the spring energy. So that's the answer. Marking scheme is in front of you. So let's move to the next question. Hopefully you understand. Okay, so the next question coming up on your screen, he says equal volumes of metal, water, and air are heated from 20 degrees centigrade to 80 degrees centigrade. State whether the metal, the water, or the air expands the most. Remember this thing: when you heat, the air will expand the most. Okay, then the liquid, and then the solid. If they have the same volume, the air, the liquid, and the solid, and you provide them with the same rise in temperature, the most expansion will be in the gas, in the air. So you can write here air. Figure 3.1 is a diagram of the metal at 20 degrees centigrade. The metal is a large square sheet with a square hole at its center. The sheet lies flat on a table. On the figure 3.1, draw the outline of the sheet and of the hole after the metal is heated. Make sure that the expansion is noticeable. Okay, so here you have a metal sheet, and it's a square. It has a square hole inside it, and this is a metal sheet. So you heated it, and obviously we know that when you will heat it, it will expand. So this outer edges, this dimension, it will increase. This dimension will also increase. So, but what will happen with this hole? So the dimension of this hole, this dimension will also increase, and this dimension will also increase. So this hole will become larger. Okay, many students confuse that these sides will increase. Okay, he will easily guess that this will increase, its dimensions will increase. But about this hole, they think that it will shrink. It will not happen. It will not come close. The hole will not shrink. It will become larger because its dimension will also increase. Its length will become larger. Its width will also become larger. So this hole will become larger. Let me show you. It's a 2-mark question. Very important. Okay. So here you can see that with the red line, I have shown the new boundary of the metal. So this, you can see the outer boundary that will go out. The red line actually shows that the piece will become larger. And this hole will also become larger. Okay, because its dimensions will also increase. Length will increase, its width will increase. So the hole will become larger. So this red line basically is showing the new boundaries of that piece of metal. Hopefully you understand. Okay, so let's move to the next question. The metal has a mass of 5 kg and a density of 7.5 expo 3 kg per meter cube. Define density. Density is basically mass divided by volume. In other words, we say it's the mass per unit volume. That's the definition of the density. Then he says, calculate the volume of the metal. Give your answer to a suitable number of significant figures. So we know that the formula for the density is mass divided by volume. And the volume is equals to mass divided by density. And very easily, I know the mass, I know the density. Very easily, I can calculate this. Let me show you. Okay, so we are going to. Okay, so here we go. So question number 3A part, air will expand the most. Question number 3C, second part is mass per unit volume is known as density. You can write the formula also that density is equals to mass divided volume. Okay, the second part, he says, question number 3, he says density is equals to mass divided by volume. Volume will be mass divided by density. The mass is 5 kg, the density is 7.5 expo 3 kg per meter cube. In your calculator, you just write 5 divided 7.5 expo 3 equal. It will give you the answer 6.67 expo minus 4 meter cube. So the volume is 6.7 expo minus 4 meter cube. Hopefully you understand. Okay, so we are done with the question number 3. So let's have a look at the question number 3's marking scheme. So my dear students, on your screen, the marking scheme of the question number 3 is showing. Take your time, pause the video, and read this marking scheme carefully. It's very important to check your answers and match them with the marking scheme. Okay, so the air square larger, hole larger, mass divided by volume or mass per unit volume. And in the question number 3C, second part, the volume will be 6.67 expo minus 4 meter cube. So hopefully you understand this. Okay. The next question coming up on your screen, that's question number 4. One form of the latent heat is the thermal energy needed to melt a solid. So define the specific latent heat. Specific latent heat is the amount of heat required to convert a substance from one state to another state at a constant temperature. During that process, The temperature should not change. So the amount of heat required to convert a unit mass of an object from one state into another state, like from solid to gas, from gas to solid, like this, from solid to liquid, from liquid to solid, the amount of heat required to convert the state of unit mass of an object at a constant temperature, that's known as specific latent heat. Okay, so let me show you my answer. I have written this definition. Okay, amount of energy needed. The amount of energy needed, here I have not written needed, the amount of energy needed to change the state of one unit mass at constant temperature. The temperature should not change, and you should have unit mass. Okay, so the figure 4.1 shows one method of measuring the thermal energy needed to melt ice. The ice is contained in a glass funnel and covered with an insulator. The heater is switched on and the ice melts. The specific latent heat of fusion of ice is 3.3 expo 5 joules per kg. Calculate the energy needed to melt 5 gram of the ice. So I know the specific latent heat of fusion, that is 3.3 expo 5 joules per kg. And the ice which is melted is how much? It is, it's 5 gram. The unit here are not consistent with each other. So I will convert this 5 gram into kg and then I can use the formula. So here, here we go. Heat is equals to M into L. That's the formula, very famous formula, where heat is the heat needed, M is the mass, and L is the specific latent heat. But I told you that the mass is not consistent with in units. So I will convert the gram into kg. So if you want to convert gram into kg, you have to divide it with 1000. So 5 divided by 1000 multiplied 3.3 expo 5 equals to, and that will be 1650 joules. So 1650 joule of energy is basically needed. So this is how you do question number 4b, first part. Hopefully you understand this numerical. Let me show you. I think I have not. Yeah, hopefully you understand. Okay, so let's move to the next part. Before the heater is switched on, thermal energy from the room causes some of the ice to melt. Describe the process by which the ice gains thermal energy from the air. You see, before you have switched on the heater is here, but you have not switched it on. You have put ice in this funnel. You have put an insulator on the top. Here you have the glass funnel. So because the glass funnel, through the walls of the glass funnel, some heat from the surrounding, through the process of conduction, will come inside and it will melt the ice. It's just you have to show the process. Okay, so let me show you. Heat is conducted through the glass from atmosphere to the ice cubes inside the glass funnel. So if you want to describe this process, you can also mention that the molecules, they will absorb the heat, their vibration will become vigorous, so they will make their neighbors vibrate vigorous. We are talking about the molecules of the glass. And by this vibration, the heat will be conducted from the outer side of the glass into the inner side, and where you have the ice. So this is how you do this. Okay. So question number 4, that's the second part. I have not written the explanation, but let me show you the marking scheme now. Okay, so question number 4, A part, you can see heat, thermal energy needed to change state of the unit mass or 1 kg without change in temperature. It's very important to mention without change in temperature. If you do not mention that, you will not get full marks of the definition. So E is equals to ml. Our final answer is right, 1650 joule. And the B second part, it is a 1 mark question. He says, By conduction and mention of the glass, funnel solid, or conduction through connections to the heater, or molecular explanation of the energy traveling through the glass. So our answers are perfect. You can have a look at the marking scheme. You can pause the video. You can take your time and have a good look at this marking scheme. And I always suggest that whenever you solve a question, please check the answers, match the answers with the marking scheme. Okay, so we are going to the question number. Basically, we are on the question number 5. A microwave signal from a transmitter on Earth's surface is sent up to a satellite in the orbit and is then immediately transmitted back to Earth. So the signal went to the satellite and from satellite came back to the Earth. So it went and came back. A pulse of the microwaves from the transmitter is received back at the transmitter 0.24 seconds later. You sent the signal from the Earth, it went to the satellite, and from the satellite, it came back to the transmitter. So it went to the satellite and came back in 0.24 seconds. The speed of the microwave is 3 expo 8 meter per second. Calculate the distance from the transmitter to the Earth, on the Earth to the satellite. So you have to tell what is the distance between the Earth and the satellite. Okay, transmitter on the Earth and the satellite. Okay, it's a very easy question. Okay, so let me show you. Just remember. So the time taken by the signals to go and come back is 0.24 seconds. The speed of the signal is 3 expo 8 meter per second. The distance traveled by the signal in going and coming back will be speed into time, 3 expo 8 multiply 0.24, and you will get 7.2 expo 7 meter. So this is the distance the signal traveled in going and coming back. But their question is, what's the distance between the transmitter on the Earth and the satellite? And that will be the half of this distance, because this is the distance of going and coming back. Now we are talking about the Earth and the satellite, transmitter on the Earth and the satellite. So that will be half of this 7.2 expo 7. Just divide 7.2 expo 7 divided by 2, and you will get 3.6 expo 7 meter. Hopefully you understand this numerical. And this is a very important and famous numerical. Okay, so this was a 2-mark question. Now, a microwave signal is used in a telephone system that produces sound. Waves are described as longitudinal or transverse. Some waves are also electromagnetic. Place ticks in the table in the figure 5.1 to show whether microwaves and the sound waves are longitudinal or transverse, and to show whether they are electromagnetic. So you know that microwaves are transverse plus they are electromagnetic. Sound waves are only longitudinal. So this is where you have to put the ticks. Let me show you. Okay, so you can see the microwaves are transverse. All electromagnetic waves are transverse. So the microwaves are transverse and they are electromagnetic in nature. Sound waves, they are longitudinal. So hopefully you understand. Okay, now let's move to the next part. He says a longitudinal wave wave contains a compression. Describe what is meant by a compression. In the longitudinal wave, the compression is where the particles of the medium come closest to each other during their vibration. If they are closest to each other, that portion of the wave is known as compression. Or you can say where the pressure is largest. For example, we're talking about the sound wave. And in the sound wave, there will be some areas along longitudinal wave, some areas where the pressure will be higher as compared to the surrounding. And at some points, the pressure will be less than the surrounding. So where the pressure is larger than the surrounding, that is known as the compression. So let me show you the definition. So I have written this, okay. So in a longitudinal wave where particles of the medium are closest to each other, that portion of the wave is called compression. Okay, hopefully you understand. Okay, so the question number 5 is over. So let's have a look at the marking scheme. Okay, so distance will be 3.6 into 10⁻⁷ meter. That's the final answer. First 2 columns correct: sound longitudinal and microwave transverse. Third column, correct, microwaves, electromagnetic. Okay, third, layers, molecules, particles, spring coils close together or higher pressure than the atmosphere. This is the marking scheme of the question number 5. You can pause the video and you can take your time to read this marking scheme for the question number 5. It's very important to always check your answers and match them with the marking scheme. Okay, so here we go. A converging lens has a focal length of 3 centimeters. An object of height 2 centimeters is placed 5 centimeters from the center of the lens. Figure 6.1 shows the arrangement of the object and the lens. Okay, so here the 5 small squares represents 1 centimeter. Remember this. This is the optical center of the lens. From here, count 15 centimeter and put a dot here. That will be your principal focus. From here, the optical center, go 15 small squares to the left and put a dot there, and that will be also principal focus. So let me show you, but we have to look at the question first. He says on the figure 6.1, draw rays from the top of the object to show how the lens forms an image of the object. Make the image clearly. Okay, so let me show you how I have done this. Okay, so my dear students, first thing which we have done is this is the optical center of the converging lens. From here, I have counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So at the 15, I moved 15 small squares to the left on the principal axis and put a dot there. This red dot you can see. This is the principal focus. I will call it F. Do the same thing on this left side also. Move 15 small squares and put a dot here and name it as F. That's the first point you have to do. Okay, so this is my object. From the top of this object, they have asked us to draw only 2 rays, but I have shown all the 3 rays which are being used. Okay, so this red one, this red one starts from the head of the object, moves parallel to the principal axis. And when it comes and passes through the lens, it passes from the F on the right side. So this red one. This green line starts from the head of the object, goes from the optical center of the lens. It goes undeviated. It do not bend. It goes straight. This blue line, it starts from the head of the object. It passes from the F, which is on the left side of the lens. And when it comes and touch this lens, after passing to the lens, it goes parallel to the principal axis. So you can see this red, green, and the blue line, they intersected at this point. So here you will see the image. So this is the image. This image is real. This image is inverted. This image is magnified. You can see it's larger than the object. Hopefully you understand that how I have used the rays which started from the head of the object and are used to make the image. Okay. Then their question is calculate the linear, the B part is the image is magnified, state one other feature of the image. The one other feature of the image is that the image will be, the image is real, the image is magnified, the image is inverted. Okay, so let's see what's the next part. C part. He says calculate the linear magnification produced by the lens in this case. It's a 2-mark numerical linear magnification. Remember my words. Linear magnification you can find by 2 methods. It's the height of the image. Count how many small squares these are. Height of the image divided by height of the object. One formula. Another formula is the distance of the image from the optical center divided by distance of the object from the optical center. Okay. I have counted them. Let me show you. Okay, so here we go. So the image is real and inverted. The linear magnification is height of the image divided by height of the object. The height of the image is 15 small squares and the height of the object is 10 small squares. So I just counted the squares and it will be 1.5. So the linear magnification is 1.5. Okay. The last part of this question is, he says, state the name of one optical device that produces a magnified image as shown in the figure 6.1. We use projectors. You see, we use projectors to see movies. And we also use that slide projector, you know, we use in the class to deliver the lecture, where we put slides on the projector. So that is also an example of this. So projector is a good example of this thing. So the projector. Okay. So the question number 6 is done. So let's have a look at the marking scheme. Okay, so the marking scheme of the question number 6 is showing up. You can pause this video and you can take your time and have a good look at this marking scheme. And I always say that it is very, very important to check the marking scheme, to check your answer, your teacher's answer, even the descriptions which I am giving, the answers which I receive. Usually we make mistakes when we write the answers. And it's important to check the marking scheme, to compare your answers with the ideas which are given in the marking scheme. Okay, so let's move to the next part, the next question. Okay, a computer hard disk contains a layer of a magnetic material. Describe how a magnet is used to find out if a sample of material is magnetic or non-magnetic. You see, it's very simple. The magnetic material will be attracted to the magnet, and non-magnetic material will not be attracted to the magnet. That's the very simple test. Okay, so let me show you my written answer. Magnetic materials will be attracted to magnets, and non-magnetic materials are not attracted to magnets. Okay, so let's go to the next question. Here data is stored on the disk as a series of north poles and south poles. On the figure 7.1, figure 7.1 shows part of the hard disk. The thin layer of the magnetic material contains small regions. Each region has a north pole and a south pole. Some magnetic field lines are shown on the figure 7.1. So here you have that layer of magnetic material. So it has region 1, this is region 2, this is region 3, region 4. So every region has its north pole, south pole. So obviously they have their magnetic line. These are magnetic lines showing up here. So region 2 causes a magnetic force on the region 1. State the direction of the magnetic force on the region 1 and explain why it acts. So region 1, region 2, so you can see they're north and north is facing each other. So they will be repelling each other because the like poles repel each other. So the region 1 will be experiencing a force due to region 2 towards the left. And that's because the opposite poles repel each other. Let me show you my answer. So, okay, force on the region 1 caused by the region 2 will be towards left. Here, north and north pole are facing each other and like poles repel each other. Hopefully you understand. Okay. On the figure 7.1, draw arrows on the field lines to show the direction of the magnetic field near the boundary between region 1 and the region 2. Okay, so this is the boundary. You know, the magnetic lines always come out of the north pole. So here you put arrows there. From north, they are coming out. From this north, they are coming out. Okay, so let me show you. So you can see I have put the arrows which are showing the direction of the magnetic lines, because from the north, the magnetic lines come out and into the south they go. Hopefully you understand. Okay. Now, a coil shown in the figure 7.1 is fixed in position. So here we have a coil. I can show you. This is a coil. And this is that magnetic material and it's moving. Okay, he will tell you that it's moving. The coil in the figure 7.1 is fixed in position. The layer of magnetic material passes quickly under the coil. So that magnetic material is actually passing under that coil. A voltage is induced in the coil as some of the boundaries between the regions pass under the coil. Explain why a voltage is induced in the coil. You see, when this material will pass under this coil, the magnetic lines passing through the coil will change. The magnetic flux which is passing through the coil, it will change in direction, in size. So what will happen whenever if the magnetic flux passing through a coil will change, EMF will be induced in the coil automatically. Let me show you my answer. Magnetic flux which passes through the coil is changing. Due to this, EMF is induced in the coil. So one more question. Hopefully you understand. Okay, then their question is, suggest why the coil must be close to the layers. If the coil will be close to the layer, it will experience a stronger magnetic field. So a larger EMF will be induced. When coil is near the layers of the magnetic material, a stronger magnetic field will be experienced by the coil and a larger EMF will be induced. Hopefully you understand. That is question number 7. I hope we are done with the question number 7. So let's have a look at the marking scheme of the question number 7. Question number 7 marking scheme is showing up on your screen. You can pause the video, take your time, take good time with this, read it carefully, compare your answers, your teacher's answers, my answers with this marking scheme. Pause the video. Okay, so we are going to the next question. A fuse is one form of protection in an electric circuit. State 2 other forms of protection that are included in the household electric circuits. These may protect the consumer, the circuit, or an electric appliance. We use circuit breakers, very famous thing. And we use sometimes double insulation. We use ground wire. We use earth wire. These are some protection other than the fuse. So let me show you. Okay. So circuit breaker and double insulation, grounding, earth wire, you can name anything. Okay. So now he says the figure 8.1 shows the fuse box connected to part of a lighting circuit in a house. State how the figure 8.1 shows the wire W is the live wire. You see, live, this is W wire. And how do we know that this is the live wire? Because these fuse are connected here. The fuse are always connected in the live wire. That's a rule. We do not connect the fuse in the neutral wire. We always connect the fuse in the live wire. Because here the fuses are connected with this W wire. That's why we know that it's the live wire. Okay. Fuse are always connected in the live wire. That's why we know that the W is a live wire. That is the reason that we know that W is a live wire, because the fuses are connected there, and fuses are always connected in the live wires. Okay, so let's move to the next part. On the figure 8.1, mark with the letter S the correct position for a switch that controls both lamps. So this is the live wire. So the switch is also connected in the live wire. So this is the live wire coming in. So here's just right here S. So you can put a switch here. So when you open it, both the lamps will go off. When you close it, both the lamps will be on. Let me show you. Okay. So hopefully you can see here. Here you can put a switch here. I've labeled it this as S. He asks us to label that point S. Okay, so the next part is, then the B part will start, section will start. The rating of the fuse in the lighting circuit is 5 ampere. Explain what this means. The rating of the fuse is 5 ampere. This means that if the less than 5 ampere current will flow, go into that lighting circuit, the fuse will work, it will let the current go. But if the current will exceed from 5 ampere, the fuse will melt, it will blow, and it will cut off the supply of the current, live current, to the lighting circuit. It will isolate the lighting circuit from the live current. If the current will exceed 5 ampere, the fuse will melt, it will blow. Okay, so by this part, we are done with the question number 8, and the section A is completed. So let me show you the marking scheme first of all. So my dear students, the marking scheme of the question number 8 is showing up on your screen. You can pause the video and you can read it, and it's very important, very, very important. Even I said that your teacher give you an answer, check it with the marking scheme. Okay, if I give you an answer, check it with the marking, compare it with the marking scheme. It's very, very important. Okay, so I have already checked the answers with the marking scheme. So thank you very much, everybody. Today, in this video, we have done, how many, the section A of this paper, and today we were doing 2000 and June 2018 paper, physics 505422 paper. Today we have done section A. In this section A, we have done question number 1 to question number 8. The section B of this paper we will do in another session, in another video, and I will upload here in the same playlist, because the section B I'm also uploading into the same playlist. Okay, so I hope that this video will be some help to you, and if you think that this video is helping you, it has made the concepts of the physics easier for you, don't forget to subscribe my channel, and don't forget to like this video. If you think that this video can be beneficial for you, for your cousins, for your senior students, with your junior class fellows, share the link of this video onto your Facebook accounts, into your Instagram accounts, into your Twitter accounts. This will help me promote my channel, and that will be a great appreciation for me for this work. So thank you very much, everybody, and have a good day. It was a pleasure. And once again, I will say Happy New Year, because today 2021 is over and 2022 is coming. So Happy New Year, everybody. God bless you all. Thank you very much.